Hello. Can you hear me? I think you should be hearing me now. Oh, great. So after a long break again, now we are back again finally. Well, okay, enough. I understood. Majority hears me. If you have trouble, just refresh the page of the YouTube link. Well, normally today I was planning to discuss about the Maxwell's other equations, and as a good news, I want to tell you that in the final exams, in fact, maybe one bad, one good news for you. The bad news is, of course, you will be questioned. Oh, Anonymous Dragon made a joke. Is dinosaur anonym dino? Okay, it's very important for our class. Thank you. Well. The good news and the bad news. The bad news is that you will be responsible in the final exam from the beginning, and the good news is till Faraday's law included. And I will not ask you any question about the Maxwell's equations, which I will teach later on. And since I received personal questions about the previous chapters, I decided to modify a bit the 3 lectures we have after on. Well, today I want to make a proper analysis with you, which topics caused a lot of difficulty, and I will talk a little bit about my observations and try to define what makes you have difficulty. And finally, what I'm trying to say today and most probably the next week will be a kind of comprehensive review and to focus on the specific topics we are, you find really challenging. Voila. So, I want to start with this feedback. I don't know how many people are online at the moment. Well, so far only 69 people. Well, 69. So, I don't know. Some people are traveling due to the I received, but okay. Any questions so far? No, I think. So, it was the first my own comment. Let's look at this feedback Elma document together. The first one is about the review on the beginning of semester. Okay, good idea. Electrical field and infinitesimal measures of length, surface, volume. This is very good point. I want to do this because I recognize after receiving several questions, today I want to flash back to infinite objects, electrical field understanding. So this is okay, this is great. Gradient divergence curl, I will come back to here. And since I received a lot of questions about the extra tutorial one, and on the step 3 and number 3, pardon, And 6, I will review this tutorial page because I know it was difficult, but it was on purpose, my dear friends, because it was just before a long vacances for you, and I want to prepare something really, really challenging. Voilà. Okay, who is this anonymous dragon? He likes to joke. Okay. Um, and everything from the beginning is a little bit cruel, I think. So I think we have to bring together what could be the specific points because it's impossible for me to review everything from the beginning, step by step. Well, but I will consider that. And we have also some questions about TD8 and the TD2. We'll see those ones as well. So, any other comments you may write on this feedback file or you can write on Google Talk. My eyes are on both these documents and platforms. Voila. Okay, great. So, are you agreeing this way? For the new arrivals, I want to repeat it again. Final exam. Oh, yes, I can talk about the final exam. So it's another good news, perhaps. It will be Socrative based, surely. And but it doesn't mean like that, in the quizzes of the CM quizzes, what I mean, not MDQs, it will be not very easy ones, yes, no questions. And it will be around 50 questions, maybe a little bit less. I don't know. I didn't decide yet. Well, and you will be given maximum 90 minutes, and most probably it will require precise analysis. What I mean is, this is the bad side of Socrative platform, as you know. You make your calculations and you make a minor mistake and it causes you to find the wrong answer, and this is what I try to avoid on just good for, it's not good for you because I like to read the paper, but somehow also there are advantages of Socrative as well, so this is why I decided to use Socrative based. But if you study properly, c'est mieux que 100 MDR. So I said, please read me once again, hear me once again, my friends. I said maximum 50 questions and around 90 minutes. So, of course, I will find the exact best numbers. This is feasible for you to be evaluated fairly. Okay, so I'm on your side. Don't worry about the content. Just you ask me question, and I'm telling you. Since we have more than 3 weeks, nothing is much clear. Okay, so but I'm telling once again, maximum 50 questions, around 90 minutes, maybe more than 90 minutes. Voila. But if you listen to me carefully today and next week, I think you will be ready for the final exams. Okay? Analyzes, of course, Safia. This is what we are doing here. So, indeed, Kantan, today and the next week, this is what we will do together to dig into the, how do you say, understand what is missing in the previous topics. Voila. And MDQs, well, since we couldn't gather with my other colleagues, MDQ's coefficient is not clear yet, but final exam will be minimum 60%. So this is something you should note perhaps, but MDQs also, it will be a big exercise like in TD or small questions. Well, okay, you want more details, but I repeat once again, please stay with me today and the next week, because in the last week also I will talk about final exam, but mostly I will talk about in the last week about Maxwell's equations, which will not be included in the exam, but it is crucial for you to learn Maxwell's equations for your future career. I have to note that maybe some people think, okay, why you teach us if it's not gonna be asked? For instance, you will be given one question and you will need to analyze it, maybe 5 minutes, but for the next few questions, maybe five, I don't know yet, you will be asked from the same analysis, some parts, you know what I mean? So it's not that rocket science, huh? So just in order to understand how precise you to solve electromagnetic problem. So this is how it's gonna work, most probably. Voila. Of course, there will be some minor knowledge measuring questions, but this is it. Any other questions about final? I can receive few more questions. Is the live working? I think so, because I'm not, if you hear me, live is working. Do you hear me? If somebody says yes or no, I could be happy. Okay, good. So go ahead. I can receive a few more questions about the final exams, then we will turn the page, huh? Okay, I understood you hear me. Voila. So I'm not touching my computer. It's likely you will not hear me. Voila. So, my friends. Any question about final exams? I think it was clear. How many questions are we going to do in the final exam? Excuse me. Ismet, there will be maximum 50 questions, 50, and voila, that's it. I already answered this question. And if we are finished, I want to go to the lecture by starting to review and to discuss together. Okay, voila. I think we are done. In fact, first of all, I want to make a few comments about what could be the reasons. Okay, so. In fact, what? Questions related between each over a bit like in TDs. Okay, like an analysis for 5 questions. Voila. But please stop worrying about the final exam. I told you several times, I'm on your side. I am caring only you to perfectly understand this lecture. So don't worry about final exam. Study hard and you will be the champion. That's it. Okay, we turn the page. No more questions about the final. What are you doing here? Watch the entire B movie. What? According to all, no. Oh my God, there are plenty. Oh, are you crazy or what? Who put these things? My God, I think it's only, excuse me for my expression, but it seems like bullshit, huh? So I skip it. Okay. Voila. So, my dear friends, I want to make a few comments, why you are finding this lecture is difficult. The first thing is mathematics. My dear friends, you have problems by making calculations of derivations, mainly derivations, and the integral calculations. So this is causing you to have a how do you say, have a it lets you to take your guard when you are learning something about electrostatics. I find some mathematics is missing in your side. So how we can improve our mathematical understandings? In fact, of course, you learn it in the mathematics class, but with some extra tools, we can find a way to support at least electrostatics lecture. First of all, I want to advise you a chapter from a very beautiful book. I already told you the name, and now I am going to tell you the specific chapter. Before the final exam, if you study this very well written book's chapter, I think it will help you to improve your mathematics, I mean, at least for the vector analysis. So I'm talking about the advanced mathematics from Kreuzig, this one, and the chapter 9. So I don't know. Well. I think it was from Wiley. So I want to directly put the this one because I'm using this edition and it's very good. So I am putting it on the Ecam Talk platform. And I feel like each exercise is a new and different logic. You are totally right, but the common pattern is okay. No, you didn't hear it from me. You don't. You can find it everywhere, huh? Please read the chapter 9. There are really beautiful exercises, and it will help you. And more general advice, I'm using this book since my student time. And if you study this summertime when you have time to review your mathematical understanding, it's really gonna be a good project for your future lectures. So keep in mind this textbook. Voila. So next topic, why we have difficulty to understand. Okay, no, stop sharing this kind of links. Huh? I deleted Monsieur Maetz because it could be a little bit problematic in the future. So I don't know how I can delete it. Okay, supprimer. Excuse me, Malo, but I said my word and you can follow up after the lecture. So, and I do agree with the commentos. Sometimes the fields are canceling, sometimes they don't. Well, in fact, in this aspect, now we can start our review session together. First of all, we started, the main laws. What we learned so far are the Coulomb's law. The Coulomb's law applied to find the surrounding electrical field, and Biot-Savart's and Gauss law, if we go by sequence, and Gauss law. After we learned the most important, one of the most important things, the line integral of the electrical field, and then we start the magnetostatics, where we learned Biot-Savart's law and Ampere's law, and finally the important Faraday's law. So these are the most important laws you will use in the future, in the, Okay, so my dear friends, in the final exam, most probably you will be measured the knowledge about these specific laws. So, in fact, I want to start with not Coulomb's law because it's quite easy to pursue, because it is like, how do you say, the So I want to go for the extra tutorial page. So now let's proceed step by step. When it's time, I will go back to feedback page. So I think the first question was easy. So first, let's make a poll and try to see uh, and first on TD1 extra. So, okay, please, Nicola, don't share any similar, how do you say, I know. When I was student, I was thinking exactly you, but we have to get rid of this one. I am deleting, I apologize for that, Nicola, but don't share these kind of links. So just see my, how do you say, latest post, and I want to receive your feedback about the first 5 exercises. Just as a sample, I will solve according, sorry, Nicola, but accept it. Okay, guys, apparently, my God, from the first question, huh? Okay, here we go. My God. Okay, second question is very challenging, apparently. Okay, great. So let's start from zero, huh? Then I see you may continue to respond to the latest poll I published, and meanwhile, the greatest difficulty comes to the second question. So let's start from the scratch. What is the problem? First of all, if you want to understand what is the logic, first of all, you have to understand the geometry, the orientation of the problem or the orientation of the system generally uh, in the space. And by understanding this, you will have a possibility to select the most appropriate coordinate system first, and then the most appropriate mathematical tools. So what I am trying to say in here, we have a point charge Q is distributed uniformly around a thin ring radius B that lies in the xy plane. So let's sketch it quickly. I want to open a new presentation page, which is empty. Okay, disposition, vide. Voila. And I want to, oh, this is 2 weeks later's lecture, so I want to get rid of that. I just need to copy, it could be a little bit time taking, so because it will be like a TD session, so I need to copy a coordinate system. Okay, my friends. Control C. Okay, voila. I don't want to redo it. So here we have the coordinate system. Apparently, if it's a curvilinear object, which is called as, it's not linear, it's not like a straight line, but it is, it's like a ring, so it has curves. So this is why in mathematics it has this curvilinear name. So here this is our ring, and its radius is B. So I want to put a B. Voila. So the B. And in fact, we want to, what is the questioned one? It's laying on the xy plane. This is what we did. And locate the point on the positive z-axis and where the electric field is the strongest. So, my dear friends, Q is shared on the edges of this ring uniformly, which means that it's like a Lord of the Rings ring, huh? So inside is empty. I need to first calculate the, since it's not a point charge, I need to find the charge distribution because Q amount of charge is not concentrated on a single point like a proton or an electron. This is what you should perceive in the first step. So since it's like a straight line, I have to remember that for the one dimension objects, the charge distribution is symbolized with lambda. Voila. And lambda, and the unit is, first of all, let me put it on, coulomb per meter, since it's a one dimension charge distribution, my dear friends. And what about the numerical or parametric value in terms of Q? Q over the circumference of the ring, huh? So it is 2 pi b, voila, 2 pi b. This is it, right? So what is happening? It's causing electrical field all the medium, all the space around. And my God, okay, thanks, Antoine. I didn't see. In fact, the idea is to understand what's going on here. In fact, as I said, this charge is causing electrical field is going all the way around. I don't know, I don't want to know in a sense. I just want to, how do you say, calculate where it gonna be strongest. So all these blue lines are representing the, how do you say, unknown electrical field legends surrounding this ring, voila. So what is my question once again? What is the strongest field, electrical field point? In fact, it could be more interesting if we didn't mention that, but it was like a clue for you. In fact, when we look at this one, the first step is to define the infinitesimal charge carrying element. It is independent from the number of the dimensions of the object, what I am saying Q. There is a universal formulation to establish a link between differential electrical field and the differential charge, and over 4 pi epsilon 0. Where is my epsilon 0? Okay, epsilon 0. And what is next is the distance between 2 points. This is it. But there is a major problem with understanding this point. This is where the difficulty, I think, starts for you. The confusion with the unit vector and the distance, what it means in real life. My dear friends, this is the universal formulation to calculate the electrical field. It can be a point charge or a straight line or a volumetric component or DC machines or NAC machines, construction, anything in the world or in the universe perhaps. I don't know how it goes in Jupiter. Well, the universal expression for electric field, voila. So this is it. But in here, I discovered by time, we have difficulty to understand what is what. What I mean, what is what, my dear friends? There are two major terms valid for both electrostatics and magnetostatics. What I mean, you should decide precisely the first the source point and the field point. What are they? In fact, this is going to let you understand and resolve the problem, and it will let you to understand which logic is compatible or which mathematical tool is applicable to your problem. So the source point, we started the story with two charges. In fact, apparently, I used a very identical name. The field point could be could be assumed as observation point. So, in fact, as I said in the beginning, the electrical field is valid everywhere in this XYZ domain. But I am observing, I put my telescope where I put for this specific exercise on Z-axis. And it can be, as I said, somewhere else, but I am observing it from here. So my field point is here on this exercise. Voila. In fact, I want to make it a little bit smaller in order to save place. And I want to get rid of these arrows because it's not necessary at all now, because I don't care the rest, but just here, let's call it as P point. Now, how the things go after? In fact, if I select, let me zoom a bit, we know that this is composed of billions of charge carrying elements. But what I have to do, I have to select a no, maybe it's better to select something like this. Okay. As I said, it's gonna take a bit time, but it's good to be like this, I imagine. So these are the infinitesimal charge carrying pieces. So what I mean is okay, it doesn't work. So here it is insertion, excuse me, dq, let's say, or we already did it, dq. So it could be very easy, perhaps some of you, but it means we are starting from the beginning. I don't want to go with the last step because I know it is the point where you have difficulty. So my dear friends, if you just concentrate on this infinitesimal distance, charge carrying point, according to the laws of electrostatics, we will observe that there will be a lot of electrical field lines origined from this one, right? It will be the system. So, in fact, there will be a very important one which is gonna be affecting this one. So, in fact, what I mean is, among these arrows, I am only concentrated on this red arrow. And here, after we define the infinitesimal vector charge carrying element, I want to name it as infinitesimal charge carrying element. And also it has another name, which is the source point. Okay, so these are important arguments, global for all electrostatics and the magnetostatics problems in order to understand perfectly. And then after, there are two important things. First, you have to decide, you have to remember, according to the Coulomb's law, the distance between the source and the field point matters. And this matters in order to calculate the amplitude or the strength of the given vector, because I know that electrical field is a kind of vector, so it has a direction, it has a strength. So in here we need to calculate this part in order to find the strength of the electrical field at the selected point. And the selected point is gonna be analyzed or understood its orientation in the space by looking at its unit vector. Voila, you are right. So this is why. And let me put a few extra comments for you, my dear friends. So we need to make this one to calculate the strength. Voila. This one, strength of the field. And okay, here we go. Oops. And to know the orientation in the space. Voila. This is one point. Insertion. Voila. Now we are ready to make analysis to get to second step. After this one, first of all, we have to calculate what is the distance between each other. So now I want to put a new name for this unknown. I want to call it as R. Okay, so R is capital R, let's say, R to be the distance between the source and the field points. Voila. And are you still there? Are you enjoying what I do? So let me do it very small, and voila. Great. So my dear friends, now it's time to, you are great. Let's go for the next step. In fact, what about the, okay, it's enough. Merci beaucoup pour votre feedback. R is equal to, in fact, now I know that, first of all, the radius of the given ring or my source object is not changing by time. It's somehow constant. And what is interesting and beautiful here is that the specific to this exercise, by the way, it could be different for another exercises. This Z point is dynamic, right? So it could be here or it could be here, because my question is, where is the strongest point? So first of all, I want to make the modeling with using expressions. So what I know that B is a constant, voila, and B square plus Z square. Z square, okay, pardon, Z square. Here, what we have to keep in mind, this is constant, the B. Maybe I should note it, because I will pause here and I will take you another important problem. So here, this is constant or constant, and B is constant. Excuse me, huh? Maybe it's like this. Maybe it's not necessary, but I want to do it very, very simple way today. Constant variable. Voila. So we are talking about these things, and this will let us to understand the dynamics of the overall system. Voila, B. And Control C, tac, tac, and the Z. So my dear friends, another thing is about the unit vector. So unit vector, as I said, as we said, will let us to understand the orientation as well as the components of the cumulative electrical field at this P point. What I mean is, if you think from the point of the Newtonian mechanics, there are multi-dimensional components of any vectorial component. The velocity, the force, the acceleration, or any other physical components expressed as a vectorial component. It's exactly the same, since electrical field also a vectorial component. So I need to know the unit vector in order to understand the vectorial components. What I mean is here, let's say this red guy is composed of something like this, perhaps, and something like this. So let me use different colors in order to understand what is what. And here, what is what? The sum of vectorial sum of these two components, green and the purple one, should give me the cumulative red arrow. In here, by looking at the system, what I see that the electrical field should have a tangential component due to the field's physical appearance. What I mean more precisely, in fact, if I had possibility to animate this dq travel all around the circle, I would see that it is circulating due to its curvilinear structure, and which could be better modeled by using the cylindrical coordinate or a spherical coordinate, not a Cartesian coordinate, because it has a curvilinear structure. I repeat, it is a curvilinear structure, so I have to go beyond the Cartesian coordinate systems. So this means that when the dq starts traveling all around the ring, it will always have two components. At least one of them will be something tangential to the source point, which means 90% phase difference, well, 90% difference between the source and the or orthogonality, maybe. I don't know which term you use, tangential or orthogonal. So which will be a radial component. What I see easily is that it has, what we learned in the Cartesian coordinates, the angle rotating around the what we said, the xy axis. This angle, tac tac, is called the polar angle. And so for such a system, the polar angle, and we called it as phi, right? Voila, equation, phi, voila. So what I concluded, my dear friends, that the electrical field has two components through the polar angle as well as the z-axis. Now, this is one point. Are we clear so far? Because these are the easy steps. And well, all of them is easy after we understand. May I continue if everything is crystal clear for all? I need some feedback from you, because it's like talking alone. I need you in this case. So, thanks, my dear friends. So after I understood and resolved the field's nature, of course we can sketch the AR vector. Well, this is AR vector. Well, of course I have to normalize it. Let me do it. AR. Thanks for the question, by the way. AR vector, Control C, Control V, voila. So this is gonna be AR vector, monsieur. I want to sketch it because what we know, I want to make a specific manipulation here. Oops, pardon. So here the amplitude of the unit vector, what we know from the, mathematics, is the strength is always 1. What we do, my dear friends, we do it, and meanwhile, I think it's time to express it analytically as well. So how we analytically express, maybe it's better to put it in, it's better to put it on down. So how would we obtain the AR vector? Exactly, Dorian. In fact, we calculate, unit vector says us that its strength is 1, and which says, okay, Halil is going to this direction. So this direction doesn't have any strength. It just gives me the idea which direction am I going, either directional par de la tête d'or or directional par Dieu. So it doesn't represent all my distance from my house to Parc de la Tête d'Or, but it dedicates my velocity with my bike through that direction. I repeat, it doesn't represent my total velocity towards there. In order to understand, I have to find my velocity strength. What we do here to calculate the strength. Voila. So what is the expression? In fact, in order to calculate for electrostatics and magnetostatics problems, I need to know the coordinates, exact coordinates of point and the field vector, source and the field vectors. So I want to note them here in order to use my page wisely. So the source point is located at which point? Something XYZ or something RPZ? Of course, RPZ. I hear you, of course, RPZ, because we said that my geometry is curvilinear, so I have to stay on the curvilinear coordinate systems. Okay, so what is the coordinate of the source point? It is B, phi, and what about the Z? It's 0, right? So, and what about the coordinates of the field point? Voila, it is B is 0, phi is 0, because observation point we are talking about, and only Z component. Now, we have to keep in mind, my dear friends, this makes the electrostatics problems a little bit abstract for your minds, or for all of our minds, let me say. It's more clear that what is variable, what is not. In fact, as I said, if we had an animation to move the dq from here all around the ring, that I will see, of course, B will not move, but phi will move from this phi1 angle to phi2 plus phi1 plus 360, and 0 doesn't change, of course. And here the field point Z will be also variable. Okay, are we good to precise the coordinates of these two important points? Why the phi coordinates at the source point is phi? Because it is coming from mathematical understanding the orientations. What I mean, are you good with understanding the curvilinearity? For instance, a spiral movement of a butterfly could be expressed only by using a curvilinear coordinate system. You cannot express it in the XYZ coordinate. Impossible. You would miss some information. This is why the scientists brought us spherical and the cylindrical coordinates. And when I look at my object, it is curvilinear, and this is why I need to have an angle information. As far as I understood your question here, and which was told me that the ring lies on the XY plane, and in a mathematical knowledge, which is that the angle between circulating around the XY plane is called as the polar angle. And in our lecture, we called or we dedicated phi variable for this polar angle. Voila. The source point is not at the origin. Voila. Merci, Yves. I have okay, I pronounced again wrong. Sorry, mademoiselle. I will call mademoiselle. So, are we good, Gaëtan? Okay, je vous en prie. So I will quickly write down the unit vector because it's a little bit time consuming what we do here, but if you understand, I will sleep very happy this evening. Voila. So first of all, what we have to do, you have to normalize the distance between the source and the field points, my dear friends. In fact, if I want to calculate my unit vector from my point to the house of to the Fourier, for instance, I have to know my coordinates on the Google Maps and the coordinates of Fourier as well in Google Maps. And if I am starting from my home to Fourier, my source point will be my home and my field point will be Fourier. So if Gaëtan or Adrien, somebody, watches me coming towards them from Fourier, in fact, in this case, I have to consider the field point as the, primary thing, primary parameter. What I mean is, of course, AR will have three-dimension parameters in a sense. Yeah, you will. So, but my home is not far from Fourier. I see it from my flat. B minus 0 will be the AR component, those guys on Fourier watching me coming towards them. So, but, okay, this is gonna be, okay, I want to call this one as capital R in order to avoid any misunderstanding. So this is the unit vectors AR. I changed it to capital R, my dear friends, pay attention. So not to confuse with the cylindrical coordinates, oops, small r, voila. So AR and plus, and they will observe from Fourier phi, the variable phi, minus the, they don't have any angular movement since it will be minus 0, and this will be the phi component of my movement towards Fourier, and voila, and plus 0 minus z. Voila. So this is it. This is my unit vector. And when I normalize it, my dear friends, I will always, Safia, why it should be, 0 minus b, excuse me. You're right. 0 minus b. Merci beaucoup. By the way, I can make some mistakes, but I assume you consider it's natural. In fact, Ismet warned me, thanks to him, about something. I will talk about a very, very minor problem today as well. So this is my unit vector. Thanks to this normalization factor, which is the distance between Fourier and my home, I will find always here 1. Voila. Are we good with the unit vector? The rest is just a few more words, and then we will, it's not z minus s. Voila. I'm happy. So, great, my dear friends. So, now it's time to talk about what's going to happen if I select a secondary twin brother of my infinitesimal charge carrying element. Voila. So I want to use it dedicated green color. So this guy is the twin of my first infinitesimal charge carrying element. In fact, it will, of course, will cause electrical field all the medium as the other brother does. So it will be something like this, and it will also have a kind of components x, r, phi, z, na na na. Okay, so let me do it identical, and maybe so I think if I do it, you will understand it, I think. So it's tagged, and the unit vector, pardon. So this is how the electrostatic problems become really difficult. I want you to pay attention. Here, it will become totally another unit vector. But it's not, what I mean, it's difficult, but it's not impossible to understand. What I mean is, my dear friends, of course, this is reality. This time, Safia is traveling from the other side of Fourier, which is exactly symmetrical to my flat towards Fourier. And this time, Adrian with his goggles will see a different unit vector because somebody is coming from another point. So this is the principle, and this is the point I assume that we have difficulty to pursue or to understand totally the problem. Voila. And after this point, now it's time to define what somebody asked a very wise question I really liked, because it was the summary of the problem. Quentin asked this question. Sometimes the fields are canceling, sometimes they don't. This is the point. In fact, this is the point where we decide what is canceling or what's not canceling at all. So, my dear friends, when I look at my specific system, the twin brothers caused strength of the electrical field will not change. But only what will change, the unit vector is going to change. Which means that if somebody wanted to, or Adrian on Fourier, if wanted to calculate the cumulative velocity, mine and Safia, from symmetrical points traveling through Fourier, he would find exactly the same thing. He would calculate exactly the same thing in this exercise. What I mean is that its tangential components would cancel each other. So AR is still like this, huh? But the others would cancel each other because of their opposite direction. If you want, I can do another one in order to show what we mean. The first field point, let's say, first first point, and maybe like this it would be great. First point and the second point. And what about the coordinate of the second point? It's gonna be no, the I'm doing pardon. First point, excuse me, I should put this one to the source because only my source is changing. My observation point is not changing. Adrian is not moving from the top of Fourier, huh? Okay, voila, pardon. So, second point, selected second point. Of course, there are billions of these guys. So this is gonna be minus p minus phi minus 0 z. And first points unit vector. Voila. And the second point's unit vector. Okay, my dear friends, so second point's unit vector, voila. So it's gonna be this time 0 minus p, 0 minus phi, and nothing, z will not change, voila. So I want to remark it with the red color. So, and now we can make an analytical calculation. So what does it mean, this expression, my dear friends? It means the integral of, if you will start learning differential equations. It's beautiful. It's like Sudoku solving, huh? You will enjoy it. I have no doubt about that. So I need to calculate the integrate the both sides of the this one in order to find the cumulative electrical field, since which means mathematically the story. This is the after geometric understanding, this is the analytical proof what we are doing here. So if I integrated the left side, in the second step I will have pardon. So excuse me, electrical field. Let me start from an expression. I know it's a little bit boring perhaps for some of you, but it's better to do it this way. So the right and left side is integrated, and there is a pure, a variable electrical field expression. And still I have the right side something differential. So now what I know, dq is expressed as a function of this one. Now some of you might have, excuse me, for f, maybe it's better to do it like this. So for the first point I want to do it, the first point, electrical field for the first point. I will call it field since there is no other field in the environment. Field of the first point. Voila. So I want to call it as electrical field. Okay, E1. So it's gonna be equal to, I know that the charge distribution is given like this, and this is the differential form of charge distribution. Maybe we can express it something comme ça. So okay, maybe no, I think it will cause some problems, so I hesitate. So I want to first bring it merely like it. and then I will decide with you the limits or whatever we need to have. So here we have, what is dq? dq is expressed as, this should be capital R, by the way, because we used capital R as the distance. Voila. So are you still there? So E1 dq is equal to q over, it's not changing, it's uniform, where it finds its meaning, huh? So pi vous êtes ici, voilà. And something tricky. In fact, in some geometries, even the charge distribution is uniform, my friends. You may need to consider the charge distribution to keep as a variable or to keep it as a constant. It depends on the geometry. I repeat again, sometimes in some specific exercises, it may be constant and sometimes it may be variable. It all depends on your understanding the problem. But in our object, it is not changing. So I hope it's clear, my friends, and I copy this section. So instead of this beautiful AR vector, voila. And I want to write down this beauty here in order to voila, voila. So what we did, I hope you can follow it, huh? Because I am doing it somehow short way for making it reader friendly at later. So this is a field of the first point, field due to first point, due to the first point, not the, due to the first point, voila. The density, no, yes, C, monsieur. This is lambda. Voilà, voilà. Lambda, voilà, voilà. Aucun remplissage, red, and something comme ça. And ça s'appelle charge carry. Oopsie. Lambda, voila. Another question, my friends? Why do we replace dq with lambda? In fact, I am calculating field due to the first point. Just I want you to pay attention. Exactly. But for a single point, I repeat, field due to single point, field due to single point. And I make it red and underlined. Just to make it simpler, after we will go back to the differential element concept, what Mademoiselle said. Mademoiselle said, I think it's better to say it like this. So, Frederick and Quentin and the others who had difficulty with this point, field due to the second point. And now it's not a differential form at all, since it is a single point. Voila! So now field due to the second point will be something like this. I want to make a slight modification here in order to give you an understanding. So I want to do it. It will give a better answer to Frederick's question. So phi1 is variable. I will highlight Wait, why did you delete the integral? Yes, I will come. So by expressing this one, tac, tac, V2 Z1, it doesn't change at all, so I want to keep it comme ça. So for the ones why I deleted the integral, I am going to ask you a very simple question. Okay, 0, Control Z, 0 plus V, and this becomes 0 plus V2. So my dear friends, let's go back to the image. What we said in the very beginning, the universal expression for the electrical field. If it is a single charge carrying element, it will not have an integral form, Dorian. So in here, I started when I was geometrically trying to understand my object, I saw it is an infinitesimally small charge carrying element, which is Q over 2 pi B. Voila. The primitive of dq is q. No, not really. It is lambda, because in here, if we understand what I am trying to say, dq is equal to, well, it should be equal to dq time, lambda, in fact, it must be better, it should be better like this, lambda times dl for my one-dimensional system, the dq. Okay, so now by keeping in mind for one dimension objects, voila. So I want to put it in a bracket, so as an extra info, voila. So my dear friends, let's go back to the second page. In here, my infinitesimal, Safia and the others, please pay attention. The primitive cannot be Q because it's lambda, and lambda is Q over 2 PB. The charge is not concentrated on this specific point. It is spread uniformly all around the ring, huh? And it is as a function of the length. But the length is infinitesimally small, and so it pretends like a tiny single element, like a proton or like an electron. So this is why I selected since the beginning the first point and the second point. They can be considered like how do you say, point charges, huh? Is it okay? Why it's not primitive at all? So the portion of the charge at the phi1 point is Q over 2 pi B. Dorian, did you have answer for your question? Because it was a beautiful, wise question, and it's a critical point as well. Why I deleted the integral? Because I am calculating only this red one, not the others among the others. So my dear friends, now I go back to my, how do you say, universal expression of electrical field. This will never change, never ever, voila. So just the circumstances will change, as I said several times. So when I look at my geometry, I realize that Q1 and Q2 are, in essence, they are identical to each other. They are complementary because I said they are twin brothers with opposite character. So just they are, how do you say, equal to each other, and because they are positioned in the symmetrical points. When I look at my system from the XY plane, they are, one is standing at the minus phi1, the other one is plus phi1, and minus p, the second point, and the first point plus p. So this is a good news. And if I make a primary school summation, since integral is summation at all, just only 2 points, huh? So insertion, tuck, tuck. I know it's a little bit so easy, but just to make it, as I said, reader friendly and to make it more understandable. So now I want to sum these two guys, and this is gonna be a beautiful discovery for all of us, my dear friends. Tuck, 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 tuck. E2 is gonna be equal to this one. AR components will cancel each other. Phi components will cancel each other. Only there will be the Z components. I don't want to write down it again. Just I want to put a comment. This sum will give only Z or give pure Z component field expression. So what we call it in the electrostatic and magnetostatic problems as, where is it? We call it as symmetry. Voila. So, are we good? And now I want to go back to my problem. Now, as I said, there are billions of points, and when I sum them up from phi1 point to again phi1 plus 360, so I need to manipulate my differential form. This is just for demonstration, my dear friends, this section. So I want to put it on a small rack, a small thing like this to differentiate it from the other one. Transparence, c'est comme ça mieux, je pense. Ah non, transparence, c'est... Voilà. So I want to keep it comme ça for you to demonstrate. Now, I want to do the essential work. So to decide what is what. As I said in here, I know that dq for one-dimensional objects like a ring is expressed like this. So I want to copy this expression in here. I know now the unit vectors, radial components and the angular components will cancel each other. So could you share the slide? Of course I will do that. This is why I am doing it a beautiful way. It was the last time I was working concentrated on a presentation. It was my PhD presentation, I think. So lambda dl, voila. So now it's time to understand. As I said, EAR at the end of the day, not now, will become only Z component. Thanks to the symmetry we discovered. Voila. So here we have to know that what is DL? What is DL? DL, when I look at here, I know it from the beginning. It's a ring which could be expressed as a, how do you say, in the cylindrical or spherical coordinates. What is the variable? R, okay, RD phi, right? RD phi, am I right? I think I am right because R is not changing. So B D phi, voila. B D phi. So now things are much easier at all. I want to change it to D phi, and I have to copy this one, control cut. I want to modify, and now it's time to play a bit with the mathematics, huh? And voila, voila, voici. Voila. So what I know is phi is equal to from 0 to 2 pi, because the Lord of the Rings lords likes to wear a complete ring. They are very greedy. They don't like half ring, right? They want to have the full power. So still I love Lord of the Rings. Sometimes I watch it, by the way. Anyway, my friends, this is why it's from 0 to 2 pi. I think everybody knows it. So, and then E becomes d phi. It's not full ring. What? It fall? Yeah, definitely. Well. Okay. Okay, I think so there are some questions at this point, and I have a sip from my coffee. You know about symmetry, is it possible to just multiply by the height? Of course, Elijah. But today we decided to make it to dig into the childhood of the problems. We are making very precise autopsy to our problem. Voila. Okay, Elliot or others. Just it's about by solving several questions, you will be the experts of symmetry or asymmetry. This is a function of your mathematical understanding the nature, nothing else. Voila. Okay, I keep going then. So somebody help me. What is what? In fact, here why did you replace the L by d phi in the equation, not b d phi? Of course, it should be b d phi. Excuse me, I made a mistake. Sometimes it's happening, as I told you. And thanks for warning it. I appreciate a lot. So here it becomes r. What we did here. Oopsie, I want to copy it from here. No, pas maintenant. Control copy. So it's gonna be this one, and here it's gonna be 3 over 2, right? Because why don't you delete square on the denominator? I didn't delete because I cannot delete it. Why should I delete it? Why don't you delete the c square? C square, what is c square? R equals B. No! Capital R is dedicated to the variable distance between the field and the source. Okay. So, and R is the variable as a function of one constant radius and the variable Z. Voila! So still we keep them both. And it transformed into this form. I received a lot. Okay, monsieur. I think you like programming a lot. So b square plus z square over 3 over 2. In fact, here I merged the unit vectors normalization factor with the distance between each other. Merci everybody for responses. Now I think things becomes much easier. Thanks to symmetry, finally, if I sum everything from 0 to 2 pi, it becomes a beautiful expression. Voila. Okay, I think it's not necessary, but I will do it on purpose. Voila. Lambda is equal to what? Q over 2 pi. Where is it? 2 pi b. B dq 0 minus 2 pi. It will be 2 pi. So look at the beauty of mathematics, my friends. So, which means if you circulate all around the ring, that it will be totally Q charges. Voila. So, and what about the AR? If I make sum of all the infinitesimal charge carrying elements from 0 to 2 pi degrees, oh sorry, radian, it will be only including z component thanks to my understanding the existence of the symmetry in my specific problem. Voila, this is how we solved the first part of our question. I don't know how long it took for us. So, are we clear till this point? If somebody is not perfectly clear, please ask the question. Okay, let me make a poll and I can see if you are still alive. So, can you just respond to this poll, please, my friends? Okay, that. Okie dokie, my friends. I want feedback from the no guys, please. Even if during the first session we don't know, please do not know your response, but we have to improve. Or what we can do, we can make an exclusive session for you. But if you give me some feedback, what is the no guys? Okay, well, I try to express AZ with AR, is that correct? Okay, AZ. Yeah, why not? Theta or phi? Okay, I may receive some questions on being the angle between R and R. Ah, okay, I understood. But you have to keep in mind, monsieur, let's look at this exercise together. This is a very smart question. I really liked it. I want to look at with you from the ZY plane. So you will resolve. You will find your answer immediately. So let's carry it here, and I want to extend a bit the Y side. So if I look at from the YZ plane, what I see here, my first DQ point, and its brother, sibling brother, is in the opposite direction, right? So, monsieur, pay attention. Here, you are right. Between R and small r and the capital R, where is it? R and the, oops, pardon, small r, which is B, there is an angle, he mentioned it as theta. But it's not theta, it's theta 1. And it's variable as well, because in each movement, when you move, it will move as well. So you may, for instance, in a simulation tool on MATLAB or on Octave, for instance, you may visualize by using an array of theta and its distribution all around the ring. But this is a little bit abstract, advanced. So this is what I don't want today. But it's good to discuss, have possibility to discuss these details as well. So for your question, finally, Esteban, since you can express for a single point, a single infinitesimal charge carrying element point, but you cannot express for a cumulative sum as here, because here, which theta? Theta varies between 0 to pi, right? So it's not gonna work as you did. But for a simple point, single point, for instance, here, it's possible to express AZ in order to convert it to Cartesian coordinate system, because It's very easy to express a single point in a Cartesian coordinate, but not a curvilinear total object like this, what we have today. Is it an answer for your question? Okay. Voila. No, guys. I want to receive. I have the snapshot. If you don't ask me, I will ask you exclusively. I took the snapshot. If you unknow, we have to know this exercise perfectly, and I hope I will success. But I mean the angle between r and the distance z. Ah, you mean the azimuthal angle? Yeah, this is possible also, but it's changing as well. Look, don't you think so? Okay, let's call this angle. You mean this angle, right? So doesn't it change as well? Here it's theta 1, let's say 30%. Here will be minus 30%. Don't you think so? Okay, guys. So now we can go back to our question. This is the how do you say, result of our question. For the first step, we are not yet finished. Now we need some more mathematical understanding. So this is gonna be pure Q. Voilà. So I want to make it un peu notre couleur. Voilà. And the question is, what is the strongest point? In mathematics, you know, the derivation, not only, for instance, if you want to know the difference between your mother and yourself, you have to subtract the heights, right? This is the only understanding. In fact, in a bigger data sets like electrical field or velocity, if you derivate, it lets you to understand the difference between each data points, each measurement. So, in fact, when you derivate, when you find the subsequent data points difference, and when you make them to equal 0, it will give you the emerging marginal points. What it means is that I'm not a mathematician. I cannot express very well as your mathematical professor, but if you express comme ça, pardon, this is what you are asked. A very beautiful exercise. And you know what is variable in my electrical field expression? Only the z is variable. So, which is gonna be, if I find the derivation with respect to the z-axis, you know, because it's gonna be varying here, you know, the other components are canceling each other. What I concluded in the first part of the exercise, here I see that it's not now it has only z-axis components. Voila. When it's equal to 0, I mean the derivative with respect to the z component, the z variable, since it's the only variable in my expression, then it will let me to find the strongest electrical field in the z-axis. So this is a general knowledge. You may apply it everywhere. In fact, I assure you, even in some application algorithms, you are using this reality every day, perhaps. So it's very practical. The strongest field point on z-axis. Voila. So if it had, for instance, let's change the question at this point a bit. In fact, if it was somehow multidimensional, so this case you would need to use partial derivation, my dear friends. So In fact, do you want me to do this calculation? Because I was talking with Adrien last week. I mean, on chat, he likes to ask me questions, which makes me happy because when you ask me questions, I like to receive your questions. Voila. So, in his question, I discovered that I made the calculation in the solution manual in a different way. So I want to do the derivation calculation together with you, and then I will skip another exercise, which was where is my feedback, Elma? This review the electrical field. This one, infinitesimal measures and the infinite objects, because it's the basics for this one to improve our understanding. Voila. So let's do it very quickly then. After all, it's only a mathematical calculation. So here I have this expression, partially derivated somehow, and the voila, control dz. Okay, so which is gonna be equal to 0, and so what I do, well, first of all, the derivation of here will be a little bit tricky. So I want to do it from the beginning. So it's gonna be, if I make mistakes, please you do as well. So I wanna keep this guy in the top. Oh, I do it again and again. So stupid. So voila. So I wanna keep it only here. Control X. Epsilon 0 VQ. Okay. So 3/2 times 2z. Okay, 0 minus, by the way. 0 minus 3/2 z, voila, multiplied by b squared, this one's. Again, Kreisig will help you. So minus 2/2, right? To make it reader friendly. So did I do it correct? So divided by, maybe comme ça c'est mieux. Comme ça, tac. Voila. Divided by square of this gentleman. Square of this gentleman, tac. C'est bon? Equals to 0 still. Why don't we just say that it's the highest when the denominator knows? Proves vectors components, right? Exactly, Elijah. Philip, I didn't understand what you mean. Just say that that is the highest when the denominator is the lowest denominator. Oh, yes, you're right. It could be possible also, but I think no. Ah, wait, let me think. The denominator highest b squared, but in fact, in this case, you would name no. I think it would converge something else. We need to use the derivation, Philip. Mathematically, what it means, what you asked. I'm trying to imagine. Okay, sorry. Okay. So here you have to do derivation, and no simpler way. And finally, you will find something. I think it would be z should be either plus minus 1/. square root sqrt b 2b, right? No, something like this. Let me check the solution answer because I don't want to redo it again and again. Solutions for extra TD1. Voilà, 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 voilà. Oopsie. Voici. Ouais. C'est ça. B over 2. What I do? B over 2 meters. It's beautiful, huh? In each side, such a ring is converging, how do you say, in the both side. But we have in the each side, it has the strongest point, but it's going fading in through the infinity. Elijah, I think I answered your question. So this is the total solution for the first exercise. Are we good? Are we still alive? Great. So I hope it improved some parts. And there is one issue I want to talk with you because I am not tired at all. And at 1:30, I have a meeting with the other professors. So it was an urgent meeting. So would it be too much pushy for you if we do not give a break and block this lecture and finish it around 1 o'clock? Would it be too much for you? Or if you want, I will not join to the meeting. We will be together at 1:30 as scheduled. I made a poll. Shall we make a block? Block means to finish at 1 o'clock and we see each other next week. I will make only a quiz, a prank quiz again, just to see who participated to the course. Okay, you see my poll? You don't have to answer one by one. If you want to make us poll, we continue now and we finish at 1 o'clock, or we continue our normal schedule. Or else you could do who can and send live chat and finish. Yes, we can. Okay, understood. So no. If you could, can you just? I think there is again. Do you see my poll? I already published it. Oh my God, I think there is a problem with my connection once again. I don't know if you hear me, but my talk is not responding. Neither I see your answers. Okay, now here we go. Okay, guys, yes, we see your poll, but I cannot see. Now I see your answers, but I think I need to refresh my page. Sometimes it happens like this. Oh, voila, now here we go. Great. So, my dear friends, well. Okay, so what? Okay, let's. If you, well, it's almost 1/3 doesn't want. So let's make a schedule because if it was a few people, I would do that, but for your good, I think it's better to give a break. I will participate later on after we finish our course. So my dear friends, in the last 10 minutes of the morning session, I think we are, I didn't give a break. I hope it doesn't disturb you. But since I promised you to talk about the simulation tools, I don't want to start that second exercise in the afternoon session, we will talk about the infinitesimal objects, and I will connect it with the other things. So, but I'm happy if this exercise was very interesting to understand the charge carrying elements. In the afternoon, we will dig into a little bit more details, maybe. So where is my FEMM? So I just want to show you as a entertainment, huh? In the last, we can do it after the meeting. No. Maybe somebody wants to travel. I mean the rest of the course. I am okay. Okay, when does your renew? My meeting normally, let me check. It's supposed to be, It's supposed to be ending. It was on Google Talk, pardon. So let me see. It's ending 1:30 to 3:30. So it's exactly scheduled on ours. Anyway, I can bring back later from my colleagues. So, okay, my friends, come back to the class. As I said, this is just extra, just an entertainment before the lunch break for us. So I want to apply what we did on this exercise. By the way, I have to save it to send it to you. I'm calling it review. Where is the lectures? Spring electrostatics CM review at 29th of May. Voila, I will send it to you. Now I want to show you this rings, how do you say, all electrical field. So in the FAMM environment, maybe some of you have already obtained it. So we start by, okay guys, okay, my friends, because I made a poll and 47 said yes for blocking, but 17 said no. And if it was again the no guys was a few people, I would do block, but I don't want 17 people to lose concentration. So I will not join my meeting. I will give a break in a few minutes after I make this simulation with you, which is very quick. And then we will be back at 1:30. Voila, it's the period. Voila. Okay, guys, I go back to my problem. So first of all, in this environment, you decide which kind of problem you are struggling with. In the as we look at here, it can be used your magnetic problems, electrostatic problems. Even you can use in the thermodynamic exercises, but I have not knowledge much about the thermodynamics, so it's not my business. So I start by selecting the electrostatic problem. Voila. In here, we have something like this. And if you move the cursor, I don't know if you can pay attention. When I move my cursor, I am working on a Cartesian coordinate system. I want you to see. And if you notice, it is in the XY plane. X numbers and the Y numbers are changing. So, in fact, first of all, I have to decide the coordinate system, because when I go back to my first sketching, I see that the charge carrying element is represented on the cylindrical coordinates. So what I do is problem definition first. In the problem segment, I open a problem segment, problem definition, axisymmetric, what it means, which represents the cylindrical coordinates, my dear friends. So when I do it, now I will see our z-plane view. So when I go back to my representation here, if I look at from the RZ plane, it will be the representation of my system. So the top view should show me the phi angular changement. So in the Cartesian coordinate system, in our representation, because it's not identical on the FEMM, so it's like looking at my object from the XY plane. So I think it's clear, I hope. So first of all, in here there are some sketching tools. You see here dots, connecting two dots linearly, connecting two dots curvilinear way. So first of all, you have to pinpoint the working environment. So you, because imagine this white surface is considered as a, how do you say, infinite plane, infinite RZ plane. I have to limit my simulation to run in a limited area. So by clicking on tab, you can define the coordinate point as one limit point. And let's say it's between 0 to, for instance, 0 to 10 centimeters, okay? I will explain again. So 0 to, voila, 0, 10 to 10. This is nothing, so I am doing it very quickly. So now I defined maybe centimeters depth, so smart mesh on, okay, 10, and the grid view keyboard. And from the view option, you can define how the environment, the infinite environments. As I said, this is just an entertainment tool for the interested ones. So by connecting 2 points, I define the, how do you say, the limits. Voila. So this is my playground, my dear friends. And this is where I will put my circular ring of the Lord of the Rings. So let's say it to be centralized, this point, what is the coordinate? 5, 5. So, or like this, something like this, something like this. Okay, not important. You can define it by clicking the mouse, but it's not so, but in order to be precise, it's better, I think, to do it like this. But when you play yourself, you will discover it's really, really easy. 4, 5, 4, 5, and 6, 5. So the right, oh no, Control Z, 6, 5, voila. So which means the radius B is by clicking on the curvilinear, how do you say, connector from here to here, which is with the angle of 180 degrees, and from here to here to complete again 180 degrees. Voila. So this is my circular ring, and with a diameter of 1 centimeter, as you can see here. Oh, sorry, radius of 1 centimeter. So now I have to define what is what. What I mean is here there is a green object. This lets me to define the environment to be, for instance, air, to be vacuum, to be, how do you say, mica, to be any environment, or water, for instance. So I have to define what is it. In fact, here, from the properties, from the materials library, you may find several parameters with certain permeability and permittivity as well. So you can carry it, my model materials. So here I select it with the right mouse, and voila, in the block type, it's gonna be considered as air, the environment. And also, when I look at my problem, the inside of the ring is also air. It's not anything else. It's empty. It's a ring. So I select inside, somewhere inside, and by clicking on the space, again, it's air. Voila. So now I put everything. But what is the issue is that here, when I go back this one, it has to be carrying Q, so boundary condition you see here, or in conductor. So what they mean, I have to add some other materials, so add a property. So here, charge, let's say. What is the charge density? You know, in here you cannot make a parametric analysis. You have to give some values. So I make it 1 microcoulomb, for instance. Oh my God. Okay, excuse me. So I will finish very soon. E to minus 6, 1 microfarad. You can change these values as well, but we will come back to here later on. Okay, property. And I click on here in conduct. Pardon. I did it. I think I should conductors, pardon, add property. Voila, here. Charge. Total charge is 1 microfarad, a microcoulomb, pardon. Okay, so I select here in conductor charge, here 1 charge, voila. Now I know that this ring carries total 2 microcoulomb, voila. And here I have to know where my simulation finishes. So I have to make here sorry, I go back to boundary because I have to know what's going to happen in the infinity. In the infinity, it should be, okay, I think I made a mistake. Just let me know. External materials. It's been a while. I didn't check it out, but it's okay. I think it's working like this. So I'm a little bit stressed because I'm stealing your time. But people who are not interested in FEMM may leave. See you afternoon, huh? I will finish very soon. So voila, boundary. And now it should work. Control save. Voila, exercise 2. TD1 extra one. So now, in fact, here, if you analyze it by clicking on this button, and you can view the results from here. Voila. So now what we see here is the voltage distribution. You can change it by using here electrical field density just to see the strength, not the vectors. So here it is, voila. So this is beautiful. And now we can view the vectors, electrical field intensity vectors. Somehow they will be represented, comme ça. Well, but keep in mind, you are looking at the ring from the top. If you could follow what I did in the FEMM simulation, it could be useful when you are designing, how do you say, any machine, any, for instance, capacitor or whatever. It could be very useful for you to find information about your object. So this is very easy tool, and it could be in the industry, you will use more advanced tools like ANSYS, like how do you say, there are really advanced tools. So this could be as a good introduction for you to shape your professional life, how do you say, ancillaries, voila. So it's it, I can publish it as well, this simulation on Espace, and you can play on it by changing the things. And the course starts at 1:30 p.m. and je vous souhaite un très bon, non, bon appétit, voilà. Voilà. So I'm ending the this session. Okay, ciao, à tout à l'heure.